So now we'll look at an algorithm for solving the linear programming problem, and we'll use the Brewer's problem as an example. This algorithm was developed by George Dantzig right after World War II, and it was in response to a very important practical problem, which was the logistics of the Berlin airlift. And again, scarce resources, in particular constraints, and you want to maximize an objective function. This algorithm that was developed by Dantzig, again, is very, very widely used today, and certainly one of the top 10 scientific algorithms ever, I'd say. So it's a very simple generic idea. We're going to start at some extreme point, and then we're going to perform this operation called pivoting that moves us from one extreme point to an adjacent one that at least doesn't decrease the objective function. And we just keep going until we get stuck. We're at an extreme point that is not better than any of its adjacent ones. Then we've got an optimal solution. So in our Brewer's problem, we start at the origin and just simply move from one extreme point to the other until we find an optimal solution. And what's remarkable is that really linear algebra sets us up to do this solution. You're familiar with solving simultaneous equations. This uses the same basic idea. The difference is that we've got many more unknowns than equations, usually, certainly not an equal number, and so we have to take care of that situation, and also we have the objective function playing a role. But still, the basic idea is to get it down to solving simultaneous equations. So there's first the idea of a basis. That's just a subset of the variables. So we pick a subset of the variables, and then we're always going to be working with something called a basic feasible solution. So the idea is you have a subset of the variables. So say that's m. In this case, there's 3 variables in the basis. And the idea is you set the other variables to 0. So now you've got m equations in m unknowns, because you just set n minus n of m to 0. And so that gives you values for your basis. The idea is that a basic feasible solution corresponds to an extreme point on the simplex. So for example, if all the slack variables are in the basis, then we set the others to 0, we set a and b to 0. Then that's what that says, that's the value of a and b when the slack variables are all in the basis. If b is in the basis and sh and sm are in the basis, then b is 0, and then if you solve for the 3 equations, you get that a equals 32, and so forth. So basic feasible solution is if you have m constraints, it's a subset of size m, so that you have an m by n system equation to solve, assuming the others to be 0. And so the algorithm, so it's called the simplex algorithm because this thing that's the intersection of all the half planes is called a simplex, and it's going to move along the simplex. So basic feasible solutions are extreme points on the simplex, and the simplex algorithm is going to move along from one point to another. Now, there's some solutions that are infeasible that are not on the simplex. It says if it's unique and feasible, it's a basic feasible solution. It could be like if you put a, b, and s sub h to be in your basis, you set the other ones to 0. It's not feasible. It's outside of the simplex, so we won't even consider those. Okay, so to get things started, what we need to do is initialize. And we'll initialize in that case at the origin when a and b are equal to 0. And the three slack variables are the basis. And then the solution is really easy in that case. Here's our equations. We set a and b to 0, so that cancels out all that stuff. So that tells us the values of SC, SH, and SM in that case. So that's easy to solve in that case. One basic variable per row, start with those as the basis, and sets our non-basic variables to 0, solve three equations, three unknowns to get the answer. You don't have to do any work for that. So that's how we initialize things, and that you can initialize right from the constraints of the problem. All that's in here is our recipe for ale and our recipe for beer, and our profit margins for the two different drinks. Okay, so now it starts to get interesting. We're going to perform an operation called a pivot. And we'll talk about how to choose the pivot in a minute. So right now, let's say we're going to choose to pivot on this entry right here. And what that means is, what we're going to do is, just as you do in Gaussian elimination, you're going to pick this element, and then you're going to solve for that variable, and then substitute that solution into all the other equations so that these entries become 0. So we solve for b equals, we take 480 minus 5a minus SC divided by 15. This equation says that's what b is. Substitute in these other equations, and that puts b into the basis and takes some other variable out. To start, you just might think about how do you figure out which variable it replaces. If we do the math here, here's what the system of equations look like. So that's just substituting a b into the other equations, including the objective function. And now our basis is b, sh, and sm. A and sc are 0. And our objective function says that z equals 736. So that's called a pivot. Pick a variable, substituting the other equations, puts it into the basis, and makes the other entries in its column 0. So why choose that particular variable? Look at the objective function, and its coefficient is positive. If we b is sitting at 0, if we increase it to some positive number, we're going to increase our objective function. So as long as the coefficient objective function is positive, that tells us the column. We could also do it on A in this case. And then why that row? You have to make sure that the right-hand side always stays bigger than 0. And so what's used is to choose the row is the minimum ratio rule. So if you take the right-hand side over the coefficient, you want the one that's smallest, because when you do the substitution, that'll make sure that the right-hand side is positive. So that's the choice of the pivots. So now we're in this situation, and we just do the same thing. So we want to look for something that's got a positive coefficient in the objective function, and then we want to do the minimum ratio rule, and that turns out to be that we pivot on column 1, row 2, and we just, that's 32 plus 4/15 SC minus SH divided by 8/3 is 3/8. Substitute that into everything, and that's going to eliminate A everywhere else, and it'll put, since we're substituting for A comes out of the basis in the objective function, and something else will go in, and again, think about what it is that goes in. And then we wind up in this situation here. So That's again just doing the math. Now, what's interesting about having done the math here, now we don't have any positive coefficients in the objective function. So these two variables are zero now, but if we take them out of the basis and get a bigger value, that's going to be no good. So we're stuck, and that's the same as saying that's the time that we stop pivoting. If we go in any direction from where we are, we're not going to do as well. And that is optimal because, first of all, any solution is going to satisfy the current system of equations. In particular, whatever values you give SC and SH, it's got to satisfy this equation. But that's going to, since they're positive, you can't do better than 800. So you might as well, you should be happy when they're zero, which is where they are. It's as simple as that. And so the current value has 800, so it's optimal. You're not going to do better. And so that's a sketch of the simplex algorithm. It's simply a matter of choosing a pivot element and then pivoting, and then keep going until you can't choose a pivot element. It's really remarkably simple when you think about it. That's the simplex algorithm for linear programming.